Right, we're going to continue working on these linear functions and patterns, and we're going to look at the difference between discrete domains and continuous domain. And if you remember, a domain is all the set of input values. So we're looking at the x in an ordered pair, right? What you would be plugging in. And if our domain is discrete, then we are looking at only certain numbers in an interval. So for example, we could have integers from 1 to 5. So we would only be talking about these 5 specific values. When I think about discrete data or discrete domain, I think about dots. Okay, so on a number line, that's one way it could look. If I was to graph on a coordinate plane, again, I'd be only graphing certain data points, so dots or distinct points. All right, I think of D for discrete and D for either dots or distinct points. That's what helps me remember what discrete is. When I think of continuous, I think of something that is all connected. So C for continuous, C for connected. And again, we're looking at the domain, so we're looking at the X or the input values. And for these, it consists of all of the numbers in an interval, not just certain points. Okay, so if we were going to graph all numbers from 1 to 5, now you don't just want the 1, 2, 3, 4, and 5, you want everything in between as well. So it's all connected. Again, if we're looking more on a coordinate plane, it will look more like this, where everything is all connected. So there's your difference between continuous domain and discrete domain. So in this next example, we are going to first decide if the data that we're going to graph is discrete or continuous. So look at your X, how it's labeled. It is labeled hours kayaking. So think about, could you kayak for just 2 hours, 4 hours, 6 hours, 8 hours, or could you potentially kayak for, any number of hours in between these points? And so, because you could kayak for, let's say 3.5 hours or 4.25 hours, right? Anything in between would make sense too. This one is going to be continuous. It would make sense to connect our points when we're all done graphing. So let's go ahead and set up our scale and graph the points. All right, you can see here that I have chosen a scale, and just when you're choosing a scale, make sure that you want to start at 0, and then whatever you go up by, you just want to keep it consistent all the way throughout on both the X and as well as the Y axis. So again, I just plotted these ordered pairs: 2 600, 4 1200, 6 1800, and 8 2400. You'll also notice that your X and Y axes were already labeled for you, so that's an important thing to do if they're not already labeled ahead of time. And then I also connected those points, right? Because again, this was continuous domain. You can have a number of hours that you'd be kayaking for between 2 and 4 hours, between 4 and 6, and between 6 and 8. So connect them all with a ray, and then to write that linear function, now we're looking at either the table of information or the graph. You can get your M and your B from either place. On the table, If I look for the change in y, it looks like y is always going up 600 as x is going up by 2. And so m is 600 over 2, which is 300. On the graph, I can see where that line is crossing the y-axis. It's right here at 0. And so that makes my b 0. So our equation is y equals 300x. There's your linear function relating y, or calories burned, to x. So now that we have an equation, we should be able to figure out how many calories you would burn in 4.5 hours. We might be able to figure that out by looking at the graph on the number of hours. So on the x-axis, I would go over to where 4.5 is, and I would read up on the graph to wherever that point is. And so I could make a guess, but if I want to get accurate, then instead I could just plug it in to the equation, which again, we just wrote that. It's y equals 300x. And since we know 4.5 hours is what we're plugging in, and hours is on the x-axis, x will be replaced with 4.5. So we're looking for the number of calories burned, or the y, when x gets replaced with 4.5. So if you do that math right there, multiply 300 times 4.5, you get 1,350. So you would burn 1,350 calories. Sometimes using your graph is fine. And again, here it looked like that was going to be a little bit more of an estimation. And so plugging it into an equation like this, that is usually going to be a more accurate answer. All right, next, why don't you try this one? Follow kind of the same process where you're going to graph, decide if it's discrete or continuous, write that equation or that linear function, and then plug in 5.5 hours and answer a question. Pause the video and then come back and see how you did. All right, take a look at your answers and see how you did. I've got it graphed. Again, how you set up your scale could be a little bit different. Just you want to make sure that your axes are labeled. Hours on the x-axis, calories burned on the y-axis. You got that from right here. And then make it consistent, right? So then plot these as your ordered pairs. And it does make sense that this is continuous because you can rock climb for, let's say, 4.5 hours, and if you do, the number of calories is changing accordingly, right? So, continuous domain. To write that linear function or that equation, again, I kind of looked for the change in y and put it over the change in x and reduced. Or, I mean, you could use the graph. Might be easier to use the table in this example. So, looks like we're going up 1,950 while we go up 3 hours. So 1,950 calories burned in 3 hours. That simplifies to 650 calories burned in 1 hour. And again, it's got a b value of 0, or a y-intercept of 0. So here's your linear function, or your equation. Y equals 650x. Now, if you want to know how many calories you'll burn in 5.5 hours, just replace this x with 5.5 and do the math. So 650 times 5.5 is 3,575 calories burned after 5.5 hours rock climbing. All right, let us know if you have any questions.